Somewhere, in the autumn of 2004, someone is still at their desk long after they meant to leave. In front of them, a graph is doing something it isn't supposed to do. A star, 41 light-years away, is wobbling. Very slightly, very rhythmically on a schedule far too regular to be an instrument fault and far too small to be anything dramatic. It's the kind of signal you could talk yourself out of if you wanted to. They don't talk themselves out of it. They just sit there at the wrong hour of the night looking at a wobble that refuses politely, but absolutely, to go away. We'll get back to them. Human beings like categories. We can't really help it. Hand us a big enough pile of anything, and within about 10 minutes we've split it into smaller piles with labels on. Animals, plants, clouds, stars. And for a good long while, planets seem to sort themselves just as obligingly. Small rocky worlds close to their stars, big gas giants further out. Sizes might vary, but the categories held, right up until astronomers started finding planets around other stars, at which point the universe, with what can only be described as quiet enthusiasm, began taking our confidence apart one discovery at a time. First came the hot Jupiters, gas giants the size of Jupiter itself, orbiting closer to their stars than Mercury does to ours, apparently unbothered by the fact that nothing that large is supposed to survive that close without slowly boiling away. Then rogue planets, drifting through the dark with no star at all, apparently unbothered by that either. Then ocean worlds, then lava worlds, entire planets, where the ground has considerably more in common with a beverage than a solid. It turned out astronomy had significantly undersold the universe's imagination. And then, 41 light-years away, in a solar system with rather more planets than seems strictly necessary, astronomers found something that has spent the last 2 decades refusing to behave. Not because the people studying it are careless, they are, if anything, almost suspiciously thorough, but because every time they think they've finally settled what this planet actually is, it hands them 2 new questions and declines to comment further. You might expect a planet capable of causing this much professional agony to have a name with a bit of drama to it. It doesn't. It's called 55 Cancri E, which is less a name than a filing reference, the astronomical equivalent of naming your firstborn client number 4. Astronomers, it turns out, save every last drop of their creativity for the science and none whatsoever for the paperwork. Tonight, we're going to meet this planet several times over, and every time we meet it, it will be a slightly different planet. A rocky twin of Earth, a world of compressed diamond, an ocean of molten stone, a planet with an atmosphere, a planet with none at all. Not because anyone has been lying to you, but because nobody has ever actually looked at this place directly. Not once, not for so much as a fraction of a second. And everything you're about to hear has been built, patiently and carefully, out of a shadow crossing a star once every 18 hours, and a small handful of stolen photons. That's not a spoiler. That's rather the whole point of tonight. Hello, and welcome to the Sleepy Astronomer. I'm so glad you're here. This is a show about the universe, the vast, patient, quietly absurd universe, told slowly, in the dark, for people who find that the biggest questions make the best company once everything else has gone quiet. If your curiosity also wanders down to the ground beneath your feet, the sleepy geographer has been mapping rivers, mountains, and the long biography of the Earth itself in the same unhurried way. And if it's the living world that pulls at you, the sleepy biologist has been exploring that territory too, one strange and wonderful creature at a time. Tonight we're going somewhere small, fast and thoroughly disagreeable, a rocky world less than 2 million kilometres from its star, close enough that an entire year there comes and goes in about the time it takes you to watch 2 feature films back to back, assuming you didn't fall asleep during the first one, which, given the show you're currently listening to, seems statistically likely. By the end of the story, you may find yourself slightly less certain than you started about what a planet actually is, and considerably more sympathetic toward the people whose job it is to find out. So, find your most comfortable position, let the room go quiet, and let's go back to a rather ordinary desk on a rather ordinary night in 2004, where someone is about to notice a wobble that simply will not leave them alone. To understand exactly what was so irritating about that graph, it helps to rewind a little further, to a slightly less complicated few decades, when solar systems were, on the whole, considered rather well behaved. Ours certainly seemed to follow the rules nicely. 4 small rocky worlds huddled in close to the Sun, Mercury, Venus, Earth, Mars, like people standing a bit too near a bus stop heater. Then a gap, filled mostly with rubble that never quite committed to becoming a planet, and has spent 4.5 billion years drifting around as a compromise instead. And then, much further out, the big ones. Jupiter, Saturn, Uranus, Neptune, enormous balls of gas and ice, keeping a polite and enormous distance from the Sun, from each other, and from all the smaller, rockier drama happening closer in. It's a tidy layout, and it has a tidy explanation. Close to a young star, it's simply too hot for anything except rock and metal to hold together. So that's what the inner planets are built from. Further out, past a boundary, astronomers rather grandly call the frost line. It's cold enough for ice to survive, and ice, it turns out, is an excellent building material. Enough of it piles up that a planet can grow large enough to start pulling in gas by the enormous, greedy handful. Rocky and small where it's hot, gaseous and huge where it's cold. A sensible recipe, and for a very long time the only one anybody had ever actually seen. Even within that recipe there was room for a little snobbery. Jupiter and Saturn, built mostly from hydrogen and helium, got to keep the grand title of gas giants. Uranus and Neptune, built instead from heavier, icier material under a thinner gassy coat, were quietly demoted to ice giants, a distinction that matters enormously to planetary scientists and almost nobody else, rather like the difference between a marquess and an earl. Which is, if you think about it for slightly too long, a bit like designing a theory of cuisine after eating exactly one meal. It was an excellent meal, nobody's disputing that. But it's a sample size of one solar system, drawn from a universe that turned out to have rather more on the menu. The first hint of just how much more came in 1995, when 2 astronomers pointed a telescope at a perfectly ordinary, sun-like star called 51 Pegasi, and found a planet where, by the tidy recipe above, no planet had any business being. It was roughly half the mass of Jupiter, a proper gas giant, not a rocky afterthought, and it was orbiting its star so closely that a full year there took just over 4 days. 4 days. Mercury, the innermost planet in our own system, takes 88, and even that felt close enough to the Sun to be considered slightly reckless. The astronomers checked their instruments, then they checked them again. A gas giant that size simply could not have formed that close to its star. It was far too hot for ice, and without ice there shouldn't have been enough raw material lying around to build something so large, and yet there it was, week after week, refusing to be an error. When they finally announced it, the reaction from the rest of the field was less popping champagne and more polite, widespread suspicion, the sort usually reserved for a dinner guest who claims to have once beaten a chess grandmaster while riding a unicycle. Several colleagues assumed it was a mistake in the data. A few assumed it was something more mundane happening on the star's own surface, dressed up to look like a planet. It took other teams, pointing their own telescopes at the very same unremarkable star to confirm that the wobble was real and that the universe had, in fact, produced something the textbook said it couldn't. Astronomers, in a rare and fleeting burst of poetic energy, named this entirely new category of world the hot Jupiter, which, by the standards of a field that would later hand a planet the identity of a filing reference, counts as something close to a literary triumph. It would be another 24 years before the two astronomers behind the discovery were awarded a Nobel Prize for it, which is roughly how long it takes the rest of the world to agree that the universe was, in fact, considerably more interesting than the textbooks had assumed. And hot Jupiters, once astronomers knew to look for them, turned out to be everywhere, which raised an obvious question and an uncomfortable one. Had the universe just handed over its strangest planets first? Or was it possible that our own tidy, sensible, rocky and close solar system was the odd one out? For a while, nobody could quite say, partly because the method used to find these planets, watching a star for the almost imperceptible wobble caused by something large and close tugging on it, happens to be extremely good at spotting big, close, heavy planets, and extremely bad at spotting anything smaller or further away. It was a bit like judging the average height of a crowd by only being able to see the people standing on chairs. As instruments improved, so did the guest list, and it got considerably stranger. Rogue planets turned up next, worlds with no star at all, simply drifting through interstellar space alone, having presumably been flung out of whatever system raised them, unbothered, unphotosynthesized, and permanently uninvited to family dinner. Then came the ocean worlds, planets wrapped in liquid water many times deeper than anything Earth has ever known, entire globes without so much as a beach. Then the lava worlds, where daytime temperatures run hot enough that the ground itself gives up being a solid and starts behaving like something you'd rather not stand in. Somewhere in among all of this, astronomers also found planets orbiting not one star but two, quietly making a fairly serious dent in the number of childhood cartoons that could still be described as scientifically implausible. One by one, each new discovery filed away another assumption that had felt, right up until that point, like plain common sense. By the early 2000s, the running joke in the field, and every field has one, was that the fastest way to guarantee a planet didn't exist was to publish a paper explaining with great confidence exactly the kind of planet the universe wasn't capable of making. So, by the time our friend from a moment ago sat down at their desk in 2004, the profession had already spent the better part of a decade getting comfortable with the idea that other solar systems could be considerably stranger than ours. Hot Jupiters by then were almost old news, impressive but filed. Rogue planets, ocean worlds, and lava worlds were exotic, certainly, but at least they were exotic in a way that made a kind of sense once you knew the physics behind them. By then, too, the searching itself had become something close to routine. What had started in 1995 as one team, one star, and one deeply suspicious result had grown into dozens of teams monitoring thousands of stars, night after night, for exactly the kind of wobble that had once seemed too strange to trust. The catalogue of confirmed exoplanets, which had stood at a single entry for the first few months of its existence, had grown into the hundreds. Somewhere in among all that steady, unglamorous cataloguing, one more star, one more wobble, one more entry in a spreadsheet nobody outside the field would ever read, a modest star called 55 Cancri quietly worked its way onto the list of things worth watching. What they were looking at didn't file away quite so easily. It wasn't a gas giant sitting somewhere it shouldn't. It wasn't drifting, starless through the dark. It was small, rocky, as far as anyone could yet tell, orbiting a modest, unremarkable star catalogued simply as 55 Cancri, tucked into the constellation Cancer, in a part of the sky that had never given anyone a reason to look twice at it before. And whatever this new planet actually turned out to be, one thing was already clear from the wobble alone. It was going to take its sweet time deciding. The wobble, as it turned out, was not going anywhere. Weeks became months, months became a properly embarrassing amount of overtime, and the signal stayed exactly where it had been from the start, small, rhythmic, and stubbornly real. By the time the paperwork was finished, the wobble had a name, or at least the astronomical equivalent of one. It was a planet, and it belonged to a star already crowded enough to make you wonder how anyone kept track. 55. Cancri itself is nothing much to look at. A yellow-orange star, a little cooler and a little older than the Sun, sitting in the faint, unglamorous constellation of Cancer, which most people can only locate by first finding something more interesting nearby and working backwards. It isn't even alone out there. Trailing along at a truly enormous distance, more distant cousin than neighbour, is a small, red dwarf companion, technically bound to the same system, practically irrelevant to everything happening closer in. Astronomers, with their usual flair, call the main star 55 Cancri A. The red dwarf is 55 Cancri B. Nobody has ever needed to call it anything else, largely because nobody has ever had reason to talk about it twice. The planets, once astronomers started finding them, arrived in a sequence that says a great deal about how this business actually works. The first, a gas giant a little heavier than Jupiter, turned up in 1996 and was naturally called 55 Cancri B, because the star had already claimed the letter A by simply existing first, and nobody was rude enough to argue with that. Others followed over the next several years. C, a smaller gas giant tucked in fairly close. D, a heavyweight out on a long, slow orbit that takes over a decade to complete. And eventually F discovered wedged in between the others, apparently unbothered by how little room there was left. Each one arrived as its own small headline, its own careful measurement, its own entry in a spreadsheet that was steadily turning 55 Cancri into one of the most crowded solar systems anybody had ever mapped around another star. By the time the alphabet reached E, there were already 4 siblings on the books, discovered in the wrong order, named with the least imagination available to the English language, and not one of them anything like the planet still waiting to be properly understood. Planet E itself did not make a good first impression, in the sense that it barely made an impression at all. The initial wobble suggested a modest world on a modest orbit, a period of a little over 2.5 days. Respectable enough, nothing especially alarming. It went into the records as such, filed neatly alongside its siblings. Nobody threw a party. If anything, E was quietly considered the least interesting member of an already fairly interesting family, which, given everything that was about to happen to its reputation, is one of astronomy's better examples of getting a first impression completely wrong. Then a few years later, a pair of researchers went back through the same data with fresh eyes and found something the original analysis had missed entirely. The signal fit the 2.5-day orbit reasonably well, but it fit a completely different orbit even better. One lasting not days, but hours, 18 of them to be precise. It's the kind of mistake that's almost impossible to notice and completely obvious once someone points it out. A bit like realizing the song you've been humming to yourself for a decade is actually in a different key to the one you thought. The star's wobble had been aliased, folded over on itself in a way that let a much faster, much closer orbit hide, convincingly behind a slower one, the astronomical equivalent of a fast talker being mistaken from a distance, for someone speaking at a perfectly normal pace. 18 hours. Once that number was on the table, everybody had to sit with it for a moment. Whatever this planet was, it was orbiting its star roughly 25 times closer than Mercury orbits the Sun. Close enough that if you tried to picture the distance to scale, you'd run out of room on most kitchen tables before you'd properly place the star. If the wobble was telling the truth this time, and by 2010 everyone had learned to be a little more careful about assuming they knew what the wobble was telling them, then 55 Cancri A wasn't just close, it was absurd, and it meant that every earlier paper describing this planet's orbit, however carefully written, however politely peer-reviewed, had been quietly, confidently wrong for the better part of 6 years. Which is precisely what made the next step so tempting. If a planet is orbiting that close, and if the orientation of its orbit happens to line up correctly from Earth's point of view, then once in every trip around its star, it should pass directly in front of that star and cause an almost imperceptible dip in its light. A transit. 18-hour orbit meant 18-hour opportunities. You didn't need patience so much as you needed to be watching at exactly the right 18-hour intervals, over and over, until either something showed up or the whole revised theory quietly died of embarrassment. In 2011 it showed up, not once but twice from 2 separate teams working independently, neither one initially aware the other was closing in on exactly the same tiny dip, in exactly the same star's light, which is either an inspiring example of science checking its own homework, or a mildly awkward race to a finish line nobody had officially entered, depending on how charitable you're feeling about academic competition. Both found it, a tiny, precise, repeating dip in the star's brightness, arriving on schedule every 18 hours, exactly where the corrected orbit said it should. It wasn't much to look at, a fraction of a percent of the star's light, gone and back within a couple of hours. But it was enough. A transit doesn't just prove a planet is there. Combined with the mass already known from the wobble, it tells you the planet's size, and size plus mass gives you density, and density is where a planet finally starts confessing what it's actually made of. The numbers came back rocky, not a gas giant, not a scaled-down Neptune, but a solid world roughly twice Earth's width, and about 8 times its mass. The first small, rocky planet ever confirmed transiting a star this bright, which is a slightly clinical way of saying astronomers could, for the first time, actually study the thing in detail, rather than simply infer that it existed and hope for the best. 55. Cancri E finally had a shape, twice the width of Earth, 8 times the mass. Do the arithmetic on that and you get a world considerably denser than water, denser than most rock you'd find lying around a garden, sitting somewhere in the general neighbourhood of what you'd expect from compressed stone and iron rather than compressed gas. In astronomer language, this was the moment 55 Cancri E stopped being a signal in a data set and became a planet you could, in principle, stand on, assuming you'd first solved the rather more pressing problem of everything else about it, which, as later chapters will make painfully clear, nobody had. Somewhere in the middle of that analysis, on an ordinary night that would later be very difficult to pin down precisely in anyone's memory, one particular researcher sat looking at a light curve, the plotted brightness of the star, hour by hour, and watched a shallow, unmistakable dip appear exactly where the 18-hour math said it had to. There's a specific private kind of satisfaction in that moment, the sort that doesn't really translate into a press release, not triumph exactly. Closer to the feeling of a key turning smoothly in a lock you'd been quietly convinced was broken. They didn't say anything to anyone for a few minutes. They just sat there looking at the dip, running the arithmetic again to make absolutely sure, and then a third time, because 2.5 years of aliasing confusion has a way of teaching a person not to trust the first version of good news. Only once the numbers refused to budge did they finally lean back in their chair and allow themselves something close to a smile. A year lasting less time than most people spend at work. A rocky world twice Earth's width, 8 times its mass, orbiting so close to its star that the two of them might as well be sharing a postcode. And, for the very first time since that first uncertain wobble back in 2004, a category it seemed to actually belong to. Not a gas giant, not a wanderer, not a distant world of ice. A rocky planet, impossibly close, impossibly fast, and, as the next several years were about to prove, considerably more complicated than rocky was ever going to cover. A rocky planet, twice Earth's width, 8 times its mass, close enough to its star that a year comes and goes in 18 hours. Say that number enough times and it starts to lose its shape a little, the way any number does with repetition, so it's worth pausing here and actually sitting with what 18 hours means for a planet, rather than simply admiring it as a fact and moving briskly on. On Earth, a day and a year are 2 entirely separate arrangements. The day comes from our planet spinning on its own axis, once every 24 hours, largely unrelated to the rather more leisurely business of orbiting the Sun, which takes the better part of a year to complete. The two rhythms coexist politely, without much reference to each other. 55 Cancri doesn't get that luxury, and the reason comes down to something astronomers call tidal locking, which sounds technical and is, once you strip away the jargon, disappointingly simple. When you orbit close enough to something big enough, gravity eventually stops letting you spin freely and simply nails you into place. The mechanism itself is almost embarrassingly unglamorous. A star's gravity doesn't pull on a planet evenly. It tugs slightly harder on the near side than the far side, stretching the planet ever so slightly out of round into something closer to an egg than a ball. If the planet is still spinning independently of its orbit, that stretch bulge gets dragged along with the rotation, slightly out of alignment with the star, and the star's gravity keeps yanking it back into line, like a hand repeatedly nudging a spinning top that keeps trying to wander off center. Every nudge bleeds away a little of the planet's spin as friction and heat, and it keeps happening over and over for as long as it takes, until eventually the spin slows down enough to match the orbit exactly, and the tugging simply stops, because there's nothing left out of alignment to correct. It isn't fast, it isn't dramatic, it's just relentless, in the way only gravity has the patience to be. You've already seen this happen, incidentally, closer to home than you might expect. The moon is tidally locked to Earth, which is why it only ever shows us one face, the near side, forever familiar, printed on every calendar and coffee mug going, while the far side stays hidden, not because it's darker or stranger, but because the moon stopped being allowed to turn away from us roughly 4.5 billion years ago, and has been standing at rigid attention ever since. It's a slightly unsettling thought, once you actually notice it. Humanity spent its entire history up to the middle of the 20th century looking at exactly the same half of our nearest neighbour, without a single person ever suspecting there was another half to be curious about. Earth's gravity did that to the moon over an unhurried few 100 million years, patient, relentless, the sort of grip that doesn't need to be strong so much as it needs to never once let go. Now imagine that same slow, patient squeeze, except instead of Earth doing the squeezing, it's a star roughly the sun's own size, and instead of the moon's polite distance, the planet in question is orbiting closer than Mercury dreams of getting. The locking that took the Earth-Moon system billions of years happens considerably faster under those conditions, and 55 Cancri A has had more than enough time, several billion years of it by most estimates, to fully surrender. Which means the planet almost certainly doesn't spin the way Earth does at all. It doesn't have mornings, it doesn't have evenings, it has one face permanently aimed at its star, and one face permanently aimed away, locked into that arrangement for as long as the planet continues to exist, with the 18-hour year simply describing how long it takes to complete one very fast, very fixed lap. Picture it properly for a moment, because it's worth the effort. On one hemisphere, the star never sets. It doesn't rise either, in any meaningful sense, because rising implies it wasn't already there. Instead, it simply sits, fixed in the same patch of sky, forever, blazing down onto a landscape that has never once known a cloud passing overhead to dim it, because there has never once been a moment of relief in which to form one. No sunset ever arrives to soften the light. No stars ever become visible, because there's never a dark sky to see them against. It is, in the most literal sense available, always exactly the same moment, over and over, for as long as the planet has existed. On the other hemisphere, entirely the opposite, a night that has lasted since the planet formed, and will last for as long as it continues to exist. No sunrise ever threatening to interrupt it, just permanent, undiluted dark, held up to whatever thin scattering of starlight happens to be passing, and, if the planet is lucky enough to have kept one, whatever faint warmth and atmosphere manages to smuggle around from the blazing side to the frozen one. And between the two, there's a line. Astronomers call it the terminator, which is a rather more dramatic name than the concept strictly requires, though in this particular case it's difficult to argue the drama isn't earned. It's the border where eternal day meets eternal night, running the entire circumference of the planet, and this is the part worth holding on to. It doesn't move. Not with the seasons, because there are none. Not with the time of day, because there isn't one, not in any sense you'd recognize. On a normal, spinning planet, a line like that would sweep around the whole globe every rotation, giving everywhere a turn in the light and a turn in the dark. On 55 Cancri A, it just sits there, fixed forever, the one genuinely stable feature on a planet that is, as later chapters are going to demonstrate at some length, not otherwise known for its stability. If you stood exactly on that line, and you couldn't, not for longer than it would take several extremely expensive pieces of equipment to fail catastrophically, but indulge the thought experiment anyway, because that's rather the point of tonight. You'd be standing in the strangest weather report imaginable. Turn one way and the ground ahead of you is baking under a permanent, unblinking star, hot enough, by most estimates, to keep rock itself from staying entirely solid. Turn the other way, and the ground behind you is locked in cold that has had the entire lifetime of the planet to settle in and has clearly made itself at home. No dawn chorus in either direction, no gradual softening of light, no lazy golden hour, none of the small daily transitions that a spinning planet hands out for free. Just an abrupt, permanent handover, one face to the star, one face to the void, with you standing, quite literally, with one foot in each of two different planets that happen to share a surface. Whether there's any wind worth mentioning along that line is a separate question entirely, and a genuinely interesting one. A planet with an atmosphere thick enough to carry heat from the blistering day side toward the frozen night might, in theory, soften that harsh boundary into something more gradual, a permanent twilight zone rather than a hard edge. Whether 55 Cancri A even has an atmosphere capable of doing that particular job is a question this show is going to spend a great deal more time on before the night is through. For now, hold on to the Terminator itself as the one fixed point in a story that is, from here on, about to become considerably less fixed. Which brings us to the question the researchers studying this planet couldn't avoid for very long. How does rock survive that? Not survive in the sense of enduring hardship. Rock doesn't have opinions about hardship, but survive in the sense of remaining rock at all. A dayside baking permanently under a nearby star isn't simply warm the way a beach is warm, or even warm the way the surface of Venus is warm, which is already warm enough to melt lead on contact. Depending on exactly how close and exactly how bright the star turns out to be, temperatures on that permanent daylight side could climb well past the point where ordinary surface rock stops behaving like a solid and starts behaving like something considerably less cooperative. Not molten in the cinematic volcano documentary sense, necessarily, but softened, weakened, possibly even flowing, in ways that a comfortable, temperate day and night planet like Earth has never had to seriously consider, and has frankly never had reason to. It's a fair question, and an uncomfortable one, and it's exactly the sort of question that tends to attract a bold, confident answer long before anyone's actually earned the right to give one, which is precisely what happened next. Because in 2012, a team of researchers looked at 55 Cancri numbers, thought about what kind of rock could plausibly survive conditions like these, and came back with an answer so striking it briefly made the tidally locked 18-hour rocky super-Earth the least interesting thing anyone was saying about it. The answer, when it arrived in 2012, didn't so much solve the puzzle of 55 Cancri as replace it with a considerably shinier one. A team of researchers working through the density figures that had come out of the transit measurements, that careful arithmetic of size and mass that had already confirmed the planet was rock rather than gas, noticed something the earlier analysis hadn't fully accounted for. If you assume the planet was built the way Earth is built, layered mostly in silicate rock around a metal core, the numbers came out slightly wrong. Not wildly wrong, just persistently, stubbornly off in the way a jigsaw piece that's almost the right shape is somehow more annoying than one that's obviously the wrong shape entirely. There's a particular kind of restlessness that sets in when a number refuses to close cleanly, the sort that keeps a researcher redoing the same calculation late into the evening on the vague, nagging suspicion that the discrepancy is trying to tell them something, rather than simply being an artifact of rounding. So they tried a different recipe. What if the planet wasn't built primarily from silicate rock at all, but from something with rather more carbon in it? Carbon that, under the kind of pressure you get deep inside a planet, doesn't stay as ordinary carbon. Push carbon hard enough, for long enough, and it rearranges itself into graphite, and then, if you keep pushing, into something considerably more famous, diamond. Run the numbers on a 55 Cancri built substantially from carbon rather than silicate rock, and suddenly the awkward jigsaw piece clicked neatly into place. The density fit, the mass fit, the whole planet, according to this particular model, could plausibly contain a mantle of graphite and diamond wrapped around a core of iron, with a third of its entire mass potentially made of carbon in one form or another, an amount that, if it were somehow all compressed into gemstones, would comfortably outweigh every diamond ever mined on Earth, by a margin too large to be worth calculating precisely. There was, buried a little deeper in the paper than the headlines ever bothered to look, an honest and rather important complication. A single number, bulk density, mass divided by volume, is not on its own enough to tell you exactly what a planet is made of. Several very different internal recipes can produce the same average density, The way a scale can tell you a suitcase weighs 20 kilograms without telling you whether it's full of books or bricks or, hypothetically, a smaller and more confused suitcase. A silicate planet with an unusually large iron core could plausibly weigh in at roughly the same density as a carbon-rich planet with a smaller one. The diamond model wasn't the only structure that fit the data. It was one structure that fit the data, a genuinely striking one, worth taking seriously, but not on the evidence available in 2012, the only honest answer on the table. That distinction between a model consistent with the numbers and the confirmed truth of the matter turned out to matter rather more than anyone quoted in the news coverage that week had time to explain. You can probably guess what happened next, because it is exactly what happens whenever a scientific paper contains both the words planet and diamond anywhere within its first paragraph. The actual research, careful, conditional, hedged with the kind of academic caution that fills entire paragraphs with words like potentially and under certain assumptions, made it about as far as the press release before all of that caution was quietly left behind at the door. By the time the story reached the wider world, 55 Cancri A wasn't a rocky super-Earth, with an interesting carbon-to-silicate ratio that might, under a particular set of modelling assumptions, contain significant graphite and diamond. It was, simply and gloriously, the diamond planet. Headlines arrived within hours, the way headlines about diamonds tend to. Astronomers watched their careful hedge, a planet that could plausibly be rich in carbon, get filed down, word by word, into a phrase with roughly the scientific precision of a fortune cookie. It is, in fairness, a genuinely wonderful image, and there's no real shame in the world running away with it a little. Picture it properly. A planet where the ground itself, deep down, isn't silicate rock at all, but layer upon layer of compressed graphite, and beneath that, under pressures no laboratory on Earth could hope to replicate, outside a diamond anvil the size of a coin, actual diamond, not scattered in seams the way it is here, but making up a genuine fraction of an entire world. It's the kind of image that makes for an excellent magazine cover, and a slightly misleading planet in roughly equal measure. Whatever was happening at that scorching, tidally locked Terminator line from the last chapter, it was apparently happening on top of a planet that could, in a very literal sense, be worth more than every currency ever printed, assuming you could somehow get to it, mine it, and then find literally anyone in the universe willing to buy several billion tons of the stuff without crashing the market so thoroughly the whole enterprise became pointless, which is, admittedly, a very specific problem to have, and one that no economist has yet been asked to seriously model. Somewhere in the middle of all this, the paper's lead author found themselves fielding a phone that would not stop ringing. Radio producers, morning television, a magazine that wanted quite earnestly to know whether this meant Earth could one day mine 55 Cancri A for jewellery, a question that requires ignoring a distance of 41 light-years, with a confidence usually reserved for people who haven't quite grasped what a light-year actually measures. Another outlet asked, with what sounded like genuine hope, whether the planet might one day affect diamond prices back on Earth, apparently picturing some kind of interstellar supply chain problem for jewelers. They answered the same handful of questions patiently over and over, gently reintroducing the words potentially and under certain assumptions back into every sentence they'd been so carefully removed from, with roughly the success rate you'd expect from trying to put toothpaste back in the tube. At one point, according to colleagues who were there for it, they were asked directly whether they were now, personally, rich. They said no. They said it slowly, the particular slowness of someone who has explained the same thing several dozen times that week and is beginning to suspect explaining it a several dozen and first time isn't going to change the outcome. Somewhere behind the patients, you got the sense they found the whole business at least a little bit funny. The way a 9-month research project involving spectral analysis and equation of state modelling had been quietly reduced in the public imagination to a planet-sized engagement ring. It's worth pausing here on what this whole episode says about how science actually reaches people, because it's a pattern this show's going to circle back to more than once tonight. The paper itself was never claiming certainty. It was proposing a model, one plausible internal structure among others that could explain the measurements available at the time, and doing so with the careful, hedge-everything language good science is supposed to use. None of that language survived contact with a headline, could plausibly contain significant carbon, consistent with though not conclusively distinguished from other structural models, isn't a phrase anyone puts in 40-point font. Diamond Planet is. It's shorter, it's punchier, and it has the enormous advantage of not requiring the reader to think about statistics before feeling something. And so, for a good few years, that's what 55 Cancri was, to more or less anyone who'd heard of it at all. Not a rocky super-Earth with an uncertain internal composition, but a planet made of jewels, full stop, no footnote required, no mention of the several equally plausible alternative recipes quietly sitting in the same paper's appendix. Which would be a perfectly satisfying place to leave the story, if the story had actually ended there. It didn't, because science, as this show has mentioned before and will happily mention again, has an inconvenient habit of continuing to ask questions long after everyone else has stopped listening for the answer. Other researchers, reading the same paper more carefully than the news cycle had bothered to, immediately started testing the diamond model against its rivals, poking at its assumptions, asking exactly the kind of unglamorous, unhurried questions that never make it into a headline but are, in the end, the entire point of the exercise. And the Diamond Planet, glittering and headline-ready as it was, turned out to be nowhere near finished changing its mind. Before we follow that argument any further, it's worth finishing a picture the diamond model started, because whatever 55 Cancri E turns out to be made of underneath, almost everyone studying it agreed on one thing early. The surface itself, on the permanent daylight side, was never going to be found sitting quietly as solid ground. Start with the numbers because they are worth having in front of you before the imagery arrives. Orbiting as close as it does, 55 Cancri E's dayside sits under starlight roughly 2,500 times more intense than what Earth receives from the Sun. Estimates for the surface temperature there run past 2,000 degrees Celsius, hot enough comfortably to melt iron, let alone the silicate rock that makes up most of a rocky planet's crust. For comparison, the hottest lava recorded on Earth, from the most violent volcanic eruptions we've ever measured, tops out somewhere around 1,200 degrees. 55 Cancri E's ordinary daytime, on an ordinary orbit, on an ordinary Tuesday if this planet had any use for the concept, runs hotter than our planet's absolute worst geological tantrums. Rock has a melting point. Every rock does, eventually, given enough heat. 55 Cancri E's dayside doesn't flirt with that number. It sails straight past it and keeps going, then keeps going a good deal further, then simply settles in and stays there forever, because there is no evening on the way to cool things down. Which means the ground itself, across the whole of that permanently sunlit hemisphere, most likely isn't ground in any sense that word usually implies. Picture it the way you'd picture Earth's oceans, except swap out the water for molten silicate rock, and swap out gentle tides for something considerably less forgiving. A lava ocean, kilometers deep in places, covering the entire dayside in a slow, heavy, glowing expanse, not flowing the way a river flows exactly, but shifting, folding, occasionally cracking open along fault lines to reveal something even hotter underneath, the way the crust on a very poorly stirred pot of soup gives way under a spoon. Mountains, if this planet ever had any in the ordinary sense, wouldn't so much erode on a world like this as simply give up and rejoin the ocean they came from. And even where the surface isn't fully liquid, assuming there's a solid crust anywhere at all, thin and precarious as it might be, floating on top of the deeper melt, that crust would be under constant, restless renovation. Whatever passes for a mountain here, on a planet like this, would be a temporary arrangement at best, heaved up by whatever's churning underneath, then slowly reclaimed by the same heat that raised it, in a cycle that never has an off-season to pause and let anything settle. Earth resurfaces itself the same way, technically, through plate tectonics and volcanism, but on a timescale of tens or hundreds of millions of years, slow enough that entire mountain ranges get to enjoy a good long run before erosion catches up. Whatever version of that process is happening on 55 Cancri's dayside is running on a clock with no seasons, no cooling nights, and no reason whatsoever to ever slow down. It's worth sitting with how strange that sentence actually is, because ocean does a great deal of quiet, comfortable work in a human vocabulary, built almost entirely around water. We picture oceans as blue, as cool, as the kind of thing you wade into on holiday, and immediately regret. An ocean of molten rock keeps the word and throws out everything else. No waves in any recognizable sense, no tide pulled by a moon, no horizon softened by haze, nothing living anywhere near it ever, under any circumstances anyone has been able to imagine. Just an enormous, glowing, planet-wide reservoir of liquid stone, radiating heat straight back out into space with the kind of intensity that would make Earth's most violent active volcano look, by comparison, like a candle someone forgot to blow out at the end of a dinner party. And an ocean like that doesn't just sit there being hot, it evaporates. Not water vapour, obviously, because there's no water anywhere near this hemisphere to speak of, but rock vapour. Minerals boiled directly out of the molten surface and lifted into whatever thin atmosphere the planet manages to hold on to. The same basic physics that makes a puddle shrink on a warm day, scaled up to a temperature where the puddle in question is made of silicate stone. Astronomers modelling this process have suggested the sky above that lava ocean could genuinely rain, in the loosest and strangest sense of the word. Not water falling from cloud to ground, but evaporated minerals condensing back out of the atmosphere and returning to the surface as something closer to fine mineral dust, or even, under the right conditions, tiny droplets of molten rock falling gently back into the very ocean they came from. It's weather, technically. It would simply be extremely unwise to stand underneath it, and considerably more unwise still to complain that you'd forgotten your umbrella, since no umbrella currently manufactured on Earth would last more than a few seconds in it. There's something almost meditative about the completeness of that cycle, if you're the sort of person who finds meditation in things that would kill you instantly. Rock melts, rock evaporates, rock condenses, high in a sky no human eye will ever see, and falls, patiently, back into the ocean it started in, over and over, on a loop that has been running, uninterrupted, for as long as the planet has existed, and shows no sign of running out of material any time soon. Earth has a water cycle, taught to every child with a diagram involving a sun, a cloud, and an arrow, pointing hopefully downwards. 55 Cancri has a rock cycle, and if anyone ever draws a diagram of it for a classroom, the arrows are going to need a rather more serious warning label. Now let's bring the Terminator back into the picture, that fixed border between eternal day and eternal night, sitting exactly where it always sits, never sweeping around the planet the way a normal day-night line would. On one side of it, this, a vast, glowing, evaporating ocean of liquid stone, hot enough to make Earth's entire geological history look, by comparison, extremely restrained. On the other side, cold, dark, and, depending on just how thick or thin an atmosphere manages to survive the trip around from the day side, potentially cold enough for whatever minerals do escape the heat to freeze solid the instant they arrive. Somewhere along that unmoving line, in theory, lava meets frost, molten rock, still glowing faintly from the heat it's carrying, edges toward a boundary beyond which the temperature simply falls off a cliff, and whatever crosses it stops being liquid rock and starts instead being something closer to volcanic glass, hardening in place the moment it drifts too far from the light that kept it molten in the first place. It's an almost impossibly strange coastline to picture, if coastline is even the right word for a border between molten stone and frozen dark. No waves breaking on it, no sand, no tide pools, no gulls arguing over the scraps of anything, because there is nothing here that ever lived to leave scraps, just glass forming in real time, at the exact latitude where heat finally, permanently runs out. A shoreline built not out of geography but out of temperature itself, holding perfectly still while everything on either side of it does something no coastline on Earth has ever had to do. Walk it, in theory, for as long as the ground allowed, and you'd have one boot slowly softening in the residual heat, while the other stayed locked in a cold that had never once in the planet's entire history been interrupted by so much as a stray beam of daylight. For now, let the picture stand as it is, because it's a genuinely useful one to carry forward. A planet with, on one side, an ocean that has never been cool enough to hold a single drop of water, evaporating itself gently into a sky that rains it straight back down, and on the other, a darkness cold enough that whatever escapes the heat doesn't so much cool down as simply stop, permanently, wherever it happens to land. Two entirely different planets, in effect, occupying the same rocky body, separated by a line that has never once moved and, as far as anyone can currently tell, never will. There's one piece missing from the picture so far, and it's the piece that decides almost everything else about it. What, if anything, sits above that glowing lava ocean? An atmosphere doesn't just sweeten the view, it moves heat around, traps it, releases it, softens extremes or makes them considerably worse. And on 55 Cancri E, it's the difference between a day side that simply bakes in isolation, radiating its heat straight back out into space the moment it arrives, and a planet that manages to share at least some of its misery with the permanently dark side across that fixed, unmoving Terminator. Whether this planet has one at all, and if it does, what's actually in it, turned out to be one of the harder questions anyone had asked about it yet. For a long time, the smart money was on nothing much at all. A planet orbiting this close to its star spent every second of its existence under a fire hose of radiation, and radiation like that is extremely good at one particular job: stripping atmospheres clean off a planet's surface, the way a hairdryer eventually empties a puddle, or the way a determined toddler eventually empties a biscuit tin, given enough time and no adult supervision. Whatever gases 55 Cancri might have been born with, the reasoning went, had almost certainly been blasted away within the planet's first few 100 million years, leaving behind bare, exposed rock with nothing but starlight for company. A simple story, a slightly bleak one, and for a while, a reasonably popular one, tidy enough to fit comfortably into a single paragraph, which, in a field this crowded with complications, counts as its own kind of appeal. Then the data started complicating it, in the way data on this planet has made something of a habit of doing. Early observations using heat-sensing instruments trained on the star system as the planet swung around it picked up something that didn't quite fit an airless world. If 55 Cancri really had nothing above its surface, the hottest point on the planet should sit directly under the star, on the exact patch of ground closest to it, with temperatures falling away steadily the further you moved from that point. The same way the warmest spot on a sun-baked pavement sits directly beneath the sun itself, no matter how you might wish otherwise. Instead, the hottest spot appeared to be offset, shifted away from the point of most direct starlight, as though something were carrying heat sideways before it had a chance to simply radiate straight back into space. Bare rock doesn't do that particularly well. It absorbs heat where it lands and re-emits it more or less on the spot, with nothing to smuggle any of it elsewhere. Moving gas does the smuggling rather efficiently, the same way a breeze on Earth carries warmth away from a sun-heated wall long after the sun itself has moved on. It was the first real hint that this planet might be hanging on to something above its surface after all, however thin. The James Webb Space Telescope, once it finally turned its attention here, gave that hint considerably more to work with. Rather than imaging the planet directly, which remains, even for an instrument this powerful, entirely out of the question, astronomers watched what happened to starlight as the planet passed behind its star, then compared it to the light received when the planet swung back into view. For a brief window, the planet's own light gets removed from the total, and by subtracting one measurement from the other, you're left with something extraordinary. The planet's contribution, isolated on its own, extracted from a combined signal that had never once actually separated the two objects visually. The difference between those two measurements carries the planet's own faint thermal signature, and buried inside that signature, the specific fingerprints of whatever gases might be doing the absorbing and re-emitting, each one leaving a slightly different mark on the spectrum, depending on exactly which wavelengths of light it swallows and releases. It's an extraordinarily delicate way of reading a world you will never see directly, built from a subtraction so precise it borders on magic trick, and on 55 Cancri A, it returned a genuinely striking result. Signs consistent with an atmosphere carrying carbon dioxide and carbon monoxide, sitting above the dayside like a thin, scorched blanket. That alone would have been remarkable enough for a planet that many had quietly written off as bare rock decades earlier. But the story got a layer stranger once astronomers started asking where an atmosphere like that could possibly have come from. This isn't the kind of atmosphere a planet is simply born with. Anything present at formation would have been stripped away long ago, exactly as the earlier bleak story predicted. What's here now, if it's really here at all, looks instead like a secondary atmosphere, one continuously replenished from below, most likely by that very same lava ocean sitting across the entire dayside. A magma ocean at those temperatures doesn't just evaporate the occasional stray mineral, as the last chapter described. It can outgas in significant quantities, venting carbon and other volatiles up from the melt the way a shaken bottle vents pressure the moment the cap comes off, except in this case the shaking never, ever stops, and there's no getting the cap back on. The atmosphere, if the model holds, isn't a leftover from the planet's birth. It's something the planet keeps actively producing, boiled directly out of its own molten surface, for as long as that surface stays molten, which, given everything covered so far tonight, appears to be indefinitely. In effect, the planet isn't wearing an atmosphere so much as continuously exhaling one, breath after breath, with no possibility of ever catching up on rest. There's more further out. Ground-based observations made years before JWST ever turned its instruments this way had already picked up faint traces of something else entirely drifting around the planet. Sodium detected not sitting neatly on the surface but spread thinly through an extended exosphere, a loose halo of atoms stretching out well beyond the planet itself, further than the planet's own gravity would ordinarily be expected to hold onto anything. The likely source, once again, traces straight back to that same relentless heat, sodium locked inside surface rock, boiled free by the same starlight cooking everything else, drifting outward until starlight pressure and the star's own particle winds slowly scatter it away into space, replenished, presumably at more or less the same rate it's being lost, in a slow, steady exchange between planet and void that has no natural stopping point built into it anywhere. A planet, in other words, not just wearing a thin atmosphere, but very gradually shedding pieces of itself into the dark around it, one sodium atom at a time, in a process that has apparently been running for as long as the planet has existed, and shows no obvious sign of stopping, or of the planet ever noticing it's happening at all. Layer all of that together, and you get a considerably richer picture than bare rock under a merciless star. A planet actively manufacturing its own atmosphere out of its own melting surface. A faint envelope of escaped sodium drifting outward into the dark, slowly bleeding the planet's own material into space around it. Carbon dioxide and carbon monoxide, detected with genuine confidence, sitting above a dayside that never once gets the chance to cool down enough to let any of it settle. Perhaps, some models suggested, even faint traces of volcanic gases riding along with the rest, vented up from wherever the melt happened to be churning, most violently that particular orbit. It's a planet, in short, that appears to be quietly exhaling, continuously, unglamorously and largely unnoticed, 41 light-years from anyone who might otherwise be paying attention. Which is roughly where the story stood for a while. Rocky, likely carbon-rich, wrapped in a thin, self-replenishing atmosphere born from its own molten surface, gently losing sodium into the dark at the edges. A genuinely coherent picture, built patiently, layer by careful layer, out of years of increasingly sophisticated observations. It even held together rather nicely. It did not, as it turns out, hold together for very long. It did not, as it turns out, hold together for very long, and it's worth for a moment stepping back from the surface of the planet entirely and looking instead at the shape of the story we've been telling about it, because that shape is stranger, in its own way, than anything happening on the lava ocean or in the thin, self-replenishing atmosphere above it. Run it back from the beginning, compressed into a single breath. A wobble, in 2004, tentatively logged as an unremarkable planet on an unremarkable orbit. A correction years later, revealing the orbit to be 18 hours rather than 2.5 days, which is less a correction and more a full retraction dressed up in more polite language. A transit, in 2011, confirming the planet as rocky, roughly twice Earth's width, considerably heavier than Earth itself. A density puzzle, in 2012, resolved by proposing a mantle built substantially from compressed carbon, graphite and diamond layered around an iron core, a planet that could, under the right assumptions, be genuinely worth more than the global economy several times over. Considerable media excitement, considerable academic caution, and a fairly wide gulf between the two. A thin, volcanically replenished atmosphere, detected with real confidence a decade later, rich in carbon dioxide and carbon monoxide, drifting above a magma ocean that never once gets the chance to cool. A faint halo of escaping sodium, drifting outward at the edges, slowly bleeding the planet's own material into the dark around it. Each entry in that list, on its own, sounds like a tidy, self-contained discovery. Stacked up together, they start to look like something closer to a diary, one written by a planet with an increasingly complicated relationship to the truth about itself. Read it all together like that, in one go, and something becomes obvious that was rather easier to miss when each piece arrived on its own, years apart, in its own separate headline. This is not the biography of a planet that has been patiently, steadily understood. It's the biography of a planet that has been re-identified from scratch roughly once every few years by people who were, at every single stage, working entirely in good faith with the best data available to them at the time. Which brings us fairly directly to the diamond, and to the rather uncomfortable business of revisiting a claim after the world has already fallen in love with it. Because if there's one part of this story that deserves a proper follow-up, rather than being quietly left to shine on in the popular imagination forever, unexamined and unchallenged, it's the part where an entire planet was, for the better part of a decade, popularly understood to be made substantially of compressed carbon. The diamond model, as the last few chapters mentioned in passing, rested on a specific and fairly elegant assumption that 55 Cancri E's interior composition would echo the composition of the star it orbits, in roughly the same way a child's overall build tends to echo a parent's. Specifically, the model leaned on the star's carbon-to-oxygen ratio, a chemical fingerprint astronomers can read directly out of starlight, which, according to the measurements available in 2012, appeared to run unusually high. A star rich in carbon relative to oxygen should, by most planet formation theories, build planets rich in carbon relative to oxygen too. Take that assumption, run it through the density puzzle from Chapter 4, and the diamond planet more or less assembles itself. Except the star's carbon-to-oxygen ratio, it turned out, had itself been measured with less precision than anyone entirely appreciated at the time. Stellar spectroscopy, reading a star's chemical makeup out of the exact wavelengths of light it emits and absorbs, is a genuinely difficult business, sensitive to exactly which spectral lines you choose to measure, exactly how you calibrate your instrument, and a small library of other technical decisions that sound minor individually and add up to something significant in aggregate. It's a bit like trying to work out the exact recipe of a meal by smelling it from the next room over. Entirely possible to get useful information that way, but the margin for a slightly mistaken guess is considerably wider than anyone standing in the actual kitchen would be comfortable with. Later studies, working with improved techniques and more carefully selected spectral lines, went back to 55 Cancri A and came away with a rather less dramatic number. Its carbon-to-oxygen ratio, on the newer measurements, looked considerably closer to the Sun's own, unremarkable ordinary, nothing like the carbon-rich outlier the diamond model had originally leaned on. Pull that supporting beam out from underneath the theory, and the whole elegant structure it was propping up starts to look rather less certain than the headlines had ever let on. None of which proves 55 Cancri E isn't carbon-rich. That's important to say plainly, because it's the part that's easiest to get wrong in the retelling. This isn't a case of one paper being right and another being wrong, so much as the ground both papers were standing on shifting slightly beneath them both. It simply means the specific chain of reasoning that made the diamond model so persuasive in 2012, an unusually carbon-heavy star, therefore plausibly an unusually carbon-heavy planet, turned out to rest on a stellar measurement that hasn't held up nearly as well as the planet's own fame did. The diamond planet didn't get disproven exactly. It got quietly, thoroughly unrecommended, the scientific equivalent of a 5-star restaurant review getting revisited by a second critic who orders the same dish and can't quite understand what all the fuss was about. And the composition question wasn't the only thing that kept shifting underfoot. Even the planet's basic dimensions, the numbers that had seemed so refreshingly solid earlier tonight, turned out to depend rather more than anyone would like on how precisely astronomers understood the star itself. A planet's measured radius, remember, comes from comparing how much starlight dims during a transit to the size of the star being dimmed. Get the star's size slightly wrong, and the planet's calculated size shifts to match, however careful the original transit measurement actually was. It's a strange kind of dependency when you sit with it. The planet's own dimensions, as far as anyone on Earth can say, aren't really a property of the planet alone. They're a property of the planet and the star together, bundled into a single calculation, wobbling slightly whenever either half of that pairing gets remeasured. As instruments improved and the host star's own properties got pinned down more precisely over the following decade, 55 Cancri's radius nudged, and nudged again, never wildly, but often enough that anyone trying to hold a single fixed picture of this planet in their head has had to keep quietly redrawing it every few years, like a police sketch being revised as new witnesses keep arriving with slightly different accounts of the same face, each one sworn, sincerely, to be the accurate one this time. If you were being uncharitable about it, you might say 55 Cancri has one of the least stable professional reputations of any planet ever discovered. A rocky twin, then a diamond world, then probably not a diamond world, then a world with a volcanic atmosphere, all inside a stretch of time shorter than most people spend paying off a car, with its own basic dimensions redrawn somewhere in the middle for good measure. If it kept a CV, it would need updating almost annually, and no interview panel on Earth would know quite which version of the applicant to expect. If you were being fair about it, and this show would gently suggest fairness is the better instinct here, you'd say something closer to the opposite. That watching a single planet get reconsidered this many times, this openly, is one of the more honest things science does in public. Nobody buried the earlier versions. Nobody quietly deleted the diamond paper once the carbon-to-oxygen measurement got revised, and nobody pretended the correction had been the plan all along. Each new measurement got laid directly alongside the old ones, in full view, footnoted, dated, attributable, and the story adjusted accordingly. In public, the way a story that's actually chasing the truth is supposed to, rather than the way a story gets told once someone's decided in advance what the ending needs to be. Still, laid end to end like this, the pattern does start to raise a slightly different, slightly more uncomfortable question than what is 55 Cancri actually made of? Because every single one of these revisions, the corrected orbit, the density puzzle, the diamond claim, the carbon-to-oxygen walkback, the atmosphere, the sodium, the nudging radius, arrived not from someone travelling out to the planet and taking a proper look, but from somebody, somewhere staring at a graph or a spectrum or a light curve and inferring an entire world from it. Every single fact you've been handed tonight has come the same way, second-hand, filtered through instruments, arriving as light rather than as landscape, which raises a question this show has been quietly setting to one side for 6 chapters now, and can't put off any longer. How, exactly, do you get to know a place like this? At all? Not roughly. Not approximately. What is actually sitting behind every single fact you've heard so far tonight? once you strip away the confident documentary tone this show has been using to tell it to you. Here's the honest answer, laid out plainly, without the confident documentary tone this show has been quietly leaning on for the last 6 chapters to soften it. Nobody has ever seen 55 Cancri, not once, not for a fraction of a second, not as a photograph, not as a disk of light, not even as the single unconvincing smudge that stood in for Pluto for the better part of a century before a spacecraft finally closed the distance. No spacecraft is ever closing the distance here. 41 light years is not a gap current technology bridges in anyone's lifetime, and it is not a gap current technology has even attempted to peer directly across. Every glowing lava ocean, every drifting halo of sodium, every scorched Terminator line this show has walked you across so vividly over the last 2 hours exists, in its entirety, as something built rather than witnessed. Which raises the obvious, slightly uncomfortable question, built from what exactly? The answer is the flicker, the same small patient signal that's been sitting quietly in the background since the very first minutes of tonight, back at a desk in 2004, when someone first noticed a star doing something it shouldn't. It's worth walking through, properly and plainly, exactly what that flicker actually is, and exactly how much weight it's been carrying this whole time. Start with the wobble itself, because that's where this entire story began. A planet doesn't simply orbit its star while the star sits perfectly still at the centre, patient and unmoved. Gravity runs both ways. The planet tugs back, however slightly, and the star responds by tracing out its own small, answering loop, wobbling almost imperceptibly as its planet swings around it. For 55 Cancri, small as planets go, though hefty compared to Earth, that answering wobble in its star amounts to a velocity shift of a few meters per second. Walking pace. The star, 55 Cancri, an object roughly the width of 1,000,000 Earths, moves back and forth by an amount you could comfortably outwalk, and it does so predictably enough, rhythmically enough, that astronomers can extract it from the starlight itself, reading it off as a tiny rhythmic shift in the exact colour of the light arriving at their instruments, the same Doppler effect that changes the pitch of a passing ambulance siren, translated from sound into colour and detected in something 41 light-years away. That's the entire foundation the planet's existence was built on for its first several years on the books. Not a sighting, but a colour shift too small to notice with anything less sensitive than purpose-built instruments costing more than most people's houses. Then came the transit, and the transit is, if anything, an even more delicate trick. Once every 18 hours, from Earth's specific vantage point, 55 Cancri happens to pass directly between us and its star. When it does, the star's light dims, not dramatically, not in any way a human eye could ever hope to register, but by roughly 1/100%, a dip so shallow it would be like standing in a football stadium under floodlights and trying to notice that someone, somewhere in the crowd, had briefly held up a single coin between their fingers and a distant light. That's the entire signal. A fraction of a percent, repeating on schedule, buried inside the ordinary flickering and noise that any star produces on its own. Flares, sunspots, the general restless static of a ball of plasma that was never designed with anyone's convenience in mind. Astronomers have to watch that same faint dip recur over and over across dozens or hundreds of orbits, stacking each noisy little data set on top of the last until the genuine signal finally rises clear of the noise around it, the way a whispered word becomes intelligible once enough people in a crowded room happen to whisper it in unison. Extracting the planet's exact size from that dip requires knowing the star's own size with real precision, which is why, as the last chapter mentioned, every improvement in stellar measurement quietly nudges the planet's measurements along with it. The planet, in a very real sense, has never once been measured on its own. It has only ever been measured relative to something else, inferred rather than observed, at every single stage. And then there's the technique behind the atmosphere itself, which is arguably the most extraordinary sleight of hand in this entire story, so it's worth giving it a moment of proper credit rather than rushing past it. To learn anything about what's actually in the thin gas layer above that lava ocean, astronomers can't point an instrument at the planet and simply read off a spectrum, the way you might analyze a sample in a laboratory. The planet is far, far too faint and far too close to its own star's overwhelming glare for that to work, rather like trying to examine the faint glow of a match held up directly beside a lighthouse beam and somehow separate the two. Instead, they wait for the planet to swing behind the star entirely, briefly vanishing from view, and they measure the combined light of the system in that moment. Star alone, nothing else. Then they wait for the planet to reappear and measure the combined light again. Star and planet together. Subtract one from the other, carefully, patiently, across many repeated orbits to beat down the noise, and what's left over in principle is the planet's own faint contribution, its own thermal glow, and buried inside that glow the specific fingerprints of whatever gases are doing the absorbing and re-emitting. It is quite literally astronomy performed by subtraction, reading an object not by looking at it, but by looking at everything else and noticing what's missing when it briefly isn't there. There is, even now, no version of this technique that involves anyone at any point actually looking directly at the planet itself. Every vivid image this episode has handed you tonight came from some combination of those three techniques and nothing else. The molten terminator, the evaporating minerals raining gently back into their own ocean, the diamond mantle and its later, quieter unravelling, the self-replenishing atmosphere, breathing carbon dioxide and carbon monoxide up out of the melt, all of it, without exception, reconstructed from a walking pace wobble, 0.1% dip, and a careful subtraction performed across repeated orbits, each one adding a little more precision to a picture that has never once been checked against a photograph, because no photograph has ever existed to check it against. It's worth being honest about what that isn't, as much as what it is. It isn't fraud and it isn't guesswork dressed up as certainty. Every single measurement in tonight's story came with its own careful uncertainty attached, its own margin of error, its own caveats. They simply don't survive very well outside the paper they were published in. The way could plausibly contain significant carbon didn't survive contact with a headline as we saw earlier. What it is, instead, is forensic reconstruction of the most patient, most rigorous kind, building a detailed, coherent, testable picture of a place nobody will ever visit, out of nothing but light, arriving one careful measurement at a time, over 20 years, from thousands of trillions of kilometers away. Somewhere in the middle of the JWST analysis, in a room that looked considerably less dramatic than any of this probably deserves, fluorescent lighting, lukewarm coffee, several laptops open to slightly different versions of the same spreadsheet, a small team sat arguing about a single wobble in a spectral line. One researcher was fairly convinced it indicated carbon monoxide. Another thought it could just as easily be an artifact of how the data had been processed, a shadow cast by the instrument itself rather than by the planet. A third wanted to run the whole reduction again from scratch before anyone committed to either interpretation out loud, on the reasonable grounds that a coffee-fueled Tuesday afternoon is not where you want a claim about an entire planet's atmosphere to originate. Someone ordered in food that nobody quite got around to eating. Someone else pulled up a second monitor to cross-check the calibration files against a completely different observing run, just to be sure the bump wasn't something the telescope itself had introduced. It took the better part of a week going back and forth before the group agreed the signal was probably real. Probably being the operative word, printed with real seriousness into the eventual paper, right alongside the number everyone would later quote without it. Nobody in that room was watching a lava ocean glisten on a screen, or picturing rain made of rock, or thinking about diamonds at all. They were squinting at a slightly bumpy line on a graph, disagreeing politely, running the numbers a fourth time because a third time hadn't quite settled anyone's nerves, and doing the unglamorous, uncinematic work that every single vivid image in this episode ultimately traces back to however many chapters of confident scene-setting narration sit between that argument and the finished story you've been listening to tonight. That's not a confession that any of this was made up. If anything, it's closer to the opposite. A wobble you can walk pace for pace, a dip you could miss by blinking at the wrong moment, a subtraction performed over and over until the noise finally gives way to a signal. Out of exactly that, and nothing more than that, an entire planet, its shape, its likely composition, its atmosphere, its slow loss of sodium into the dark, has been coaxed into view patiently, disagreement by disagreement, correction by correction, without a single spacecraft ever leaving home. It's the most honest kind of magic trick there is, one where everyone involved tells you repeatedly exactly how it's done, and it's still somehow completely astonishing that it works at all. Knowing how the trick is done doesn't spoil it exactly, but it does change how you watch it. Go back now to the question this show left sitting quietly, whether 55 Cancri A actually has an atmosphere at all, and it reads differently than it did an hour ago. Not because the question has changed, because you now know in some detail exactly how thin the evidence supporting either answer really is, and exactly how much careful, contested work is hiding underneath every confident sentence this show has handed you so far tonight. Here, laid out honestly, is where that question actually stands. Nobody agrees, not in the sense of a field split down the middle by ideology or stubbornness, but in the much more interesting sense of several careful teams working with the same telescope, looking at the same planet, and coming away with genuinely different conclusions because the measurements themselves are sitting right at the ragged edge of what current instruments can reliably tell apart. One set of observations, the kind this episode leaned on previously, points toward a thin secondary atmosphere. Carbon dioxide, carbon monoxide, gases that would make sense for a world continuously outgassing from a molten interior, replenished as fast as starlight and stellar wind strip it away. Another set of observations taken at different wavelengths, processed with different assumptions about how to remove the star's own light from the mix, points somewhere else entirely, toward a planet with essentially no atmosphere to speak of, just bare exposed silicate rock, baking directly under starlight with nothing above it to trap heat, move it sideways, or soften the transition into the dark. Two research groups, two careful, well-reasoned papers, two pictures of 55 Cancri A that can't both be fully correct, and neither one obviously wrong. Read one paper in isolation, and you'd come away entirely convinced. Read the other in isolation a week later, and you'd come away just as convinced of something close to the opposite, and neither reaction would reflect badly on you as a reader. It would simply reflect how the papers themselves are written, each one making the strongest honest case its own data actually supports. It's worth sitting with why that's even possible, because it isn't sloppiness on anyone's part. The eclipse subtraction technique from the last chapter, measuring the system with the planet hidden, then again with the planet visible, and reading the difference, produces a signal that is, by the standards of literally any other branch of science, vanishingly small. The planet's own contribution to the combined light of the system amounts to a tiny fraction of the star's overwhelming output, and teasing a reliable answer out of a signal that faint means every choice made along the way. Which wavelengths to trust most, how to model the star's own faint variability, how to handle the inevitable gaps and glitches in any real observation, even which orbits to include and which to quietly set aside as too noisy to trust, can nudge the final answer meaningfully in one direction or another. None of those choices are arbitrary or careless. Each one gets argued over, justified, written up, defended in peer review by people whose entire professional reputation rests on getting it right. And still, two teams, both working carefully, both being scrupulously honest about their uncertainties, can end up on opposite sides of the same question, without either one having made anything resembling a mistake. There's a version of this show that would find that frustrating, and it's worth acknowledging that plenty of people do, entirely reasonably. There is something quietly maddening about following a story this closely and arriving, at the end of it, at a shrug dressed up in careful language. It would be simpler, certainly, to be told with total confidence, yes, atmosphere, here's exactly what's in it, filed and finished. But simpler and true aren't always the same shape, and a planet sitting at the genuine edge of what current instruments can resolve isn't a failure of the science. It's exactly what the frontier is supposed to look like from the inside before enough data has accumulated to settle it one way or the other. The alternative, pretending certainty that isn't there yet, simply because uncertainty makes for an awkward headline, is precisely the instinct that turned a hedged, careful paper about carbon ratios into Diamond Planet Found. And this show would rather sit with an honest, we don't know yet, than repeat that particular mistake twice in one episode. So, if there is an atmosphere, what would actually be in it, and where would it have come from? The honest answer is, it depends which model you're inclined to trust, and possibly on which day you're asking. The volcanic outgassing picture, carbon and sulfur compounds vented continuously from the magma ocean below, remains a leading candidate, and a genuinely elegant one, because it explains the atmosphere's presence and its behaviour with a single, ongoing mechanism, rather than requiring anything unusual to have happened just once, long ago. But there's a competing picture worth taking just as seriously. Not a volcanic atmosphere at all, but a rock vapour atmosphere generated directly by the evaporating magma ocean itself, with the boundary between ground and sky becoming genuinely blurry on the dayside, less a solid planet wearing a separate gas layer, and more a single continuous system of molten rock gradually turning to vapour and back again, with no clean seam between the two. Under that second picture, asking, does the planet have an atmosphere, is a bit like asking whether a simmering pot of soup has a separate layer of steam sitting on top of it, or whether the steam is simply the soup, doing what soup does at that particular temperature. The categories themselves start to blur at the edges, which is a fairly unsettling thing for a category-loving species to sit with, given how this whole episode began. Both pictures, interestingly, would produce broadly similar chemical fingerprints in the kind of spectrum JWST can actually measure, which is precisely why the disagreement hasn't resolved itself yet. It isn't a case of one team having sharper eyes than the other. It's a case of the planet itself sitting in a genuinely ambiguous zone, where two quite different physical stories can produce data that looks, from Earth, disconcertingly similar. And underneath all of that sits a further complication this show has mostly left to one side. Until now, even the question of how efficiently heat moves from the day side to the night side, the very offset hotspot that first hinted at an atmosphere earlier tonight, has itself been measured differently by different observing campaigns, at different times, with different instruments. Some measurements suggest a planet redistributing a meaningful fraction of its heat around toward the permanent dark side, consistent with a genuine, if thin, moving atmosphere. Others suggest barely any redistribution at all, more consistent with bare rock simply absorbing and re-radiating heat roughly where it lands, with nothing above it to smuggle any of it elsewhere. Even the planet's own thermal personality, in other words, hasn't held entirely still long enough to be pinned down with total confidence. Is this really happening, this delicate outgassing world with its self-replenishing sky? Or are we once again looking at a signal too faint to fully trust, and quietly filling in the gaps with the most compelling story available, the way the Diamond Planet once filled in a density puzzle with the most striking explanation on offer at the time? The honest answer tonight is that nobody currently knows for certain, and anybody claiming otherwise is doing exactly what this show spent Chapter 4 gently poking fun at. What's genuinely reassuring, if you sit with it for a moment, is that this isn't where the story stops. More observing time is scheduled. Better instruments are already being planned, designed specifically to squeeze a cleaner signal out of exactly this kind of maddening, right-at-the-edge measurement. The disagreement between these teams isn't a dead end. It's a to-do list, precisely the sort of open, unresolved argument that tends to get closed a few years down the line by whoever manages to build the next slightly more sensitive instrument, or think of the next slightly cleverer way to subtract a star's glare from a planet's whisper. Science, in that sense, is less like a courtroom reaching a single final verdict, and more like a long-running renovation project, with each generation of astronomers picking up roughly where the last one left the tools out. In 5 years, or 10, this particular chapter of 55 Cancri story will very likely have an answer it doesn't have tonight. Which means, if you're inclined to keep listening to this show that far into the future, there's a reasonably good chance you'll get to hear this exact question resolved, one way or the other, on some other quiet night, possibly by an entirely different research team using an instrument that hasn't even been switched on yet. For now, though, the honest picture is the interesting one, uncertainty and all, a planet that might be gently exhaling volcanic gases into a thin, self-renewing sky, or might be a bare, blistering rock with nothing above it at all, or might be something stranger still that nobody has quite proposed yet, sitting 41 light-years away, entirely unbothered by which explanation eventually wins, waiting, as it has for 20 years now, for the rest of us to catch up. It has, after all, absolutely nowhere else to be. Zoom out now, one last time, because 55 Cancri was never really the whole story. It's simply the planet that happened to be close enough, and bright enough, and stubborn enough about refusing to be pinned down, to make a good excuse for telling this show's actual story, that everything we assumed about planets, right back at the very start of tonight, was built on a sample size embarrassingly close to 1, our own 8 planets orbiting our own one star, mistaken for a good long while for the whole of what a solar system was allowed to look like. Go back to the introduction if you can still remember that far. Rocky worlds close to their star, gas giants further out. A tidy, sensible arrangement, and for a long time the only one anybody had any evidence for. Since then, this show has walked you through hot Jupiters, orbiting closer to their stars than they have any business surviving. Rogue planets, drifting through permanent interstellar dark, with no star to call their own. Ocean worlds, wrapped in liquid water many times deeper than anything Earth has ever known. And now, across the last 9 chapters, one particular rocky world, tidally locked, 18-hour year, glowing lava ocean on one side, and permanent frozen dark on the other, with an atmosphere that may or may not exist, made of gases nobody can quite agree on, sitting on top of an interior that might or might not contain diamond, orbited by a star with a family so crowded that half its members still can't be given a name more interesting than a letter of the alphabet. That's already a fairly extensive guest list for a universe that was, according to the tidy old recipe, only supposed to be serving 2 dishes with a strict no substitutions policy. And it isn't close to finished. Astronomers have, by now, catalogued planets that skim so close to their stars they complete an orbit in a matter of hours, atmospheres stripped down to nothing but a bare, glowing husk, trailing behind them like a comet's tail made of the planet's own evaporating self. They've found mini-Neptunes, a category that didn't even exist in our own solar system's guest list. Planets larger than Earth but smaller than Neptune, wrapped in thick hydrogen envelopes. Occupying a size bracket our own 8 planets simply skipped over entirely, as though the universe had a whole shelf of options our particular corner of it never bothered sampling. They found planets orbiting 2 stars at once, casting 2 shadows and presumably requiring twice the sunscreen. They found planets that orbit nothing at all, and planets so puffed up and low in density that if you could somehow find an ocean big enough to drop them in, they would, quite genuinely, float, bobbing there patiently like the least likely bath toy in recorded history. They found planets whose skies rain glass sideways, and planets locked so tightly to their stars that a full year passes in less time than it takes to watch the show's average episode. Put all of that together, and the tidy old categories from the introduction don't just bend a little at the edges. They collapse outright, the way a card table collapses under one leg, too many stacked casually on top of it. Planets, it turns out, don't come in 2 flavours, rocky and gaseous, close and far. They come in dozens, possibly hundreds, sorted along axes nobody had even thought to draw a line on before the first exoplanet turned up in 1995. Orbital distance, atmospheric thickness, internal composition, degree of tidal locking. Whether the world in question has 1 star overhead or 2, whether it has a star at all, whether its ground and its sky are even meaningfully different things or simply the same material at 2 different temperatures. Every single new discovery hasn't just added another entry to a list. It's occasionally forced the list itself to be redrawn, the categories widened, sometimes abandoned altogether in favour of a spectrum too continuous and too strange to sort neatly into folders. The way this show's introduction rather hopefully suggested might be possible. Human beings, as that same introduction pointed out 2 hours ago now, like categories. The universe, it turns out, was never particularly consulted on the matter, and appears to be getting on perfectly well without our input. Which leaves an uncomfortable, faintly funny question sitting right at the centre of everything. If planets genuinely come in this many varieties, this many combinations of heat and orbit and composition and company, then which one of them is actually the odd one out? For the entire length of human history up until a few decades ago, the answer felt too obvious to bother asking. Earth was the planet, the baseline, the one every other world got measured against, however implicitly, the way a tailor keeps one particular customer's measurements pinned to the wall as the standard fit, adjusting every future garment against that single familiar silhouette without ever quite noticing how unusual that customer actually was. Rocky, but not too rocky. Warm, but not molten. Orbiting at a distance close enough for liquid water and far enough to avoid becoming a second, quieter 55 Cancri A. Spinning steadily, day following night following day, with nothing remotely 18 hours about their arrangement and nothing resembling a permanent terminator anywhere on the entire surface. Except once you actually count up everything else that's out there, actively count it, planet by strange planet, rather than simply assuming Earth sits somewhere near the middle of the pack, that comfortable, ordinary-feeling arrangement starts to look considerably less like the default and considerably more like the exception, the way a single very tall person at a family gathering might, for years, have simply assumed height worked roughly the way theirs did, right up until somebody finally showed them the actual average. Most of the planet's astronomers have catalogued orbit closer to their stars than Mercury does to the Sun. A significant fraction are locked in the same permanent day-night arrangement as 55 Cancri A, one face forever lit, one face forever dark, with nothing resembling a sunset anywhere on the entire world. Many are considerably larger than Earth, sitting in that mini Neptune bracket our own solar system apparently declined to fill. Vanishingly few, by comparison, sit anywhere near Earth's own particular combination of size, temperature, spin rate, and liquid surface water. Earth's gentle, spinning, temperate, unlocked, liquid-watered arrangement, day and night, trading off politely every 24 hours, nothing evaporating, nothing glowing, nothing quietly raining rock back into an ocean of itself, might not be the sensible standard-issue planet at all. It might, on the current evidence, be the strange one, the genuine outlier, the planet that, if some patient astronomer 41 light-years away happened to be watching our own star's light dim every so often, would come away scratching their head and writing a paper wondering how on Earth, or rather, how on anywhere else, a world like this one ever managed to hold together at all, let alone hold on to oceans that never once boiled, froze, or drifted quietly off into space. There's something worth sitting within that, quietly, before this episode lets you go. Every single strange, glowing, tidally locked, atmosphere-uncertain world, catalogued across the last 2 hours, makes Earth look a little less like the obvious answer, and a little more like a genuinely improbable outcome. One very particular, very fortunate roll of a very large set of dice, sitting at exactly the right distance from exactly the right kind of star, spinning at exactly the right rate for exactly the right span of time, to end up covered in oceans that are actually made of water, under a sky that, occasionally, gently, rains the same water back down rather than molten stone. It isn't that Earth is uniquely blessed in some cosmic, purposeful sense. Nothing in tonight's story points toward purpose of any kind. It's simply that the particular combination of conditions required to produce a temperate, watery, gently spinning world turns out to be a narrow target in an enormously wide field of possibilities, and Earth, for reasons that remain a genuinely open question in their own right, happened to land on it. Somewhere tonight, on that particular improbable outcome, someone steps outside after dinner, glances up without giving it a second thought, and sees nothing unusual at all. No molten terminator, no self-replenishing sky of carbon dioxide and carbon monoxide, no drifting halo of escaping sodium, no debate raging quietly in some observatory's inbox about whether a spectral wobble means volcanic gas or bare rock or something else entirely. Just an ordinary evening, an ordinary sky, stars in more or less their usual places, entirely unremarkable to anyone who's spent their whole life inside it. They might glance toward a Cancer without knowing it, without any particular reason to look there twice. The same faint, unglamorous patch of sky that once held nothing more interesting than an ordinary yellow-orange star, right up until 2004, when it very much stopped being ordinary to at least one person, at one desk, on one otherwise unremarkable night. They go back indoors a moment later, thinking about something else completely. Dinner, probably, or a conversation from earlier in the day, or nothing at all, utterly unaware that 41 light-years away, a small, fast, stubbornly disagreeable world is still sitting there in the dark, refusing, as it has for 20 years now, to be pinned down, and showing no particular sign of starting tonight. Let's go back, one last time, to that desk in 2004. We never did properly return to them, and it feels only fair to close the loop before the night's fully over. There they still are, in the version of this story that lives permanently in your head now, leaning toward a screen later than they meant to stay, looking at a wobble that refused to resolve into noise no matter how many times they checked it. They had no way of knowing, that night, that they were looking at the first flicker of a planet that would spend the next 20 years being a rocky twin, then a diamond world, then probably not a diamond world, then a planet quietly exhaling volcanic gases into a sky nobody can fully agree exists. They just knew the wobble wouldn't leave them alone, which, if you think about it, is more or less the entire relationship anyone has ever had with 55 Cancri A. It never once behaved. It simply refused to leave anyone alone. The Terminator is still out there too, exactly where this show first found it, that fixed, unmoving line between a dayside hot enough to keep rock from staying solid, and a nightside that has never once in the planet's entire history felt anything resembling warmth. Everything else about this planet has been revised, walked back, quietly unrecommended, or left genuinely unresolved at least once tonight. The Terminator hasn't. It's the one part of this entire 2-hour story that was never actually in doubt, sitting there right now, unbothered, while astronomers on a small blue planet 41 light-years away keep arguing about absolutely everything else. And that, in the end, is really the whole shape of tonight's story, if you draw it out properly. 55 Cancri A itself hasn't changed very much since 2004. It was rocky then. It's rocky now. It was orbiting close then, absurdly uncomfortably close, and it's orbiting exactly that close now, on exactly the same 18-hour clock it's kept since long before anyone on Earth learned to notice it. What's changed, again and again, sometimes twice in the same decade, is us, our instruments, our models, our confidence, our willingness to publish a headline before the caveats had finished being written. The planet held still. We're the ones who kept getting caught changing our minds about it, in public, on the record, which is either faintly embarrassing or the most reassuring thing in this entire episode, depending on how charitably you're feeling by this point in the evening. This show began by pointing out that human beings like categories, that we sort everything, that we'd quietly assume planets came in exactly 2 tidy varieties before the universe got involved and complicated matters considerably. It's worth being honest now, at the end, about what that complicating actually adds up to. It isn't that the universe turned out to be messier than we'd hoped, or less orderly, or somehow disappointing once you got a proper look at it. It's that every single time astronomers thought they'd finally found the edge of what a planet could be, rocky here, gaseous there, simple, sensible, done, something 41 light years away, or 400, or 4,000, quietly declined to fit inside the box and kept going anyway. We don't discover, at the end of a story like this one, that the universe is simpler than we assumed. We discover every time that it's wonderfully, inexhaustibly stranger than we had the imagination to expect, and that the discovering never quite finishes. Somewhere out there tonight, that flicker is still arriving. A star, 41 light years away, dimming by 1/100%, on schedule, every 18 hours, whether or not anyone happens to be watching for it this particular week. It's been doing that for the planet's entire existence, long before 2004, long before there was anyone on this side of the signal equipped to notice. It'll keep doing it long after tonight, long after the current arguments about atmospheres and rock vapour and carbon ratios finally get settled one way or another, by someone who probably hasn't started that particular research project yet. The light left a long time ago. Some of it is only arriving now, and somewhere in between the two, patiently, unglamorously, an answer is already on its way toward us, at the only speed answers are ever allowed to travel. Sleep well, and if the strange, distant, quietly disagreeable things are the ones that help you drift off, we'll be here again next time, with another world waiting patiently in the dark, in the middle of changing its mind about something. Good night, the Sleepy Astronomer